All right, we're going to do another example for an energy conservation problem, but this one's more conceptual. Here I have a frictionless track, and there's like you could put a little roller coaster car on here. I don't know, here, we'll put a little roller coaster car on there, kind of like the ones you did on your lab. Um, if you're listening to this in years hence, never mind about that lab comment. Okay, so let's say you start here on this track with a velocity of 0. Okay, so you do not have velocity. And this car is allowed to roll down the track. Okay, so it goes woo. Okay, we're going to say that the energy due to the rotating wheels is negligible. Don't worry about it. If you're wondering what I'm talking about, don't worry about it. We haven't talked about that yet. There's no air resistance, there's no friction. It just roller coaster. This thing coasts, okay? And energy is conserved because there are no forces outside the system of the car Earth system. Alrighty? Now let's talk about some of the consequences of this. Number one, where is this thing going to be moving the fastest? So the idea here is if total energy is the same, which it is, okay, then whatever potential energy, gravitational potential energy is lost by the car, that will be gained kinetic energy. So like whatever potential energy is lost is how much kinetic is gained. So the more potential energy you can lose, the more kinetic you can gain and the faster you'll be moving. So if you're presented a problem like this and asked where is, like at what point A, B, C, D, E is the car moving the fastest, you just want to find the lowest point. That's it. So that would be C. Okay. That is the car is moving the fastest here. That's a very common, like, multiple choice problem that comes up. So they'll just give you a picture and they say, where is it fastest? They also might ask you, like, to what point does the car, like, reach? What's the highest point the car reaches? Or they might ask something like, does the car reach point, and then they'll give you a point. Okay, let's ask it that way. Does the car reach points B, C, D, E? So here's where something interesting comes up. Right now, at point A, all of the cart's energy, E, is potential plus kinetic, but there is no kinetic. So all of the energy is just the gravitational potential energy at point A. There is no kinetic. Whatever the potential energy is here, that is the total energy, and that is how much energy the cart will have for the entire run. Okay? Sometimes we'll use that to find the total energy of the cart Earth system for the entire run. If we're given like a height or something, you'll use that to find the energy. But whatever it is, there is no more. Let's say that at this point UG is say 100 joules. So that means E is 100 joules. That means energy is 100 joules everywhere else. That's what I'm saying. Okay, everywhere else, every single other point, the energy is 100 joules. Now, I'm not going to write it for E, and there's a reason for that. If you're at a height lower than this height, which I've got some nice, lovely graph paper going on here. So this height, the height of point A, if you're exactly at that height, like you are at point D, that means that your potential energy is 100 joules again. But that means that there isn't any energy left over for kinetic energy. Okay? At point A, UG was 100 and kinetic was 0. So if I'm back at that height, like at point D for instance, then I'm back with potential energy of 100 joules. I keep trying to say newtons. It is joules, not newtons. Okay? And that means that my sum, kinetic plus potential, must add up to 100, which means that kinetic must be 0. At point D, this car's got to stop, okay? And it will never make it to point E, because if the car stops right there, it can't go any higher. It has stopped. It will stop and it will fall. It will fall back the other way, okay? There's no way to get to point E, because to get there, you would need a potential energy of more than 100 joules. And that's impossible, because to do that, you'd have to get the energy from somewhere. And you might be thinking, well, just like have kinetic energy go down more. But to go down more, you'd have to have kinetic energy that's negative. And you can't have ever a kinetic energy that's negative, because kinetic energy is 1/2 mv squared, and where are you going to get the negative? You can't get a negative from 1/2. There's no negative. You can't have negative mass. While you can have a negative velocity, it immediately gets squared. So kinetic energy is always positive. So we can't borrow from it to make more potential. So I can never go higher than the point where all of my energy is potential energy, ever. Okay? In this picture, you will never reach point E. Just never. It's never going to happen. The only way to make it happen is if you somehow added energy to the system, which we will be talking about later. You'd have to do work on the system. Okay? These other points, if you could find either the potential energy or the kinetic, you could find the other one, because you have combinations of potential and kinetic. But without numbers, I can't get them exactly. Combination of kinetic and potential. Okay. Now, to be very clear, although we cannot borrow from kinetic to make more potential, we can borrow from potential to make more kinetic. There's no limit to like how far down I could go, and I could have negative potential, and then my kinetic could get really, really, really big. That's okay. All right, just to be very, very clear. Let's see, is there anything else I can ask you about this conceptual problem here? Not really. Okay, that's it for this.